Okay, so yeah, I'm Liam Connor. I'm going to be calling in. I'm going to be talking today about measuring cosmic baryons with fast radio bursts and all of the exciting extragalactic astrophysics one can do with these measurements. I saw this cartoon a couple weeks ago. It made me laugh. It also made me grateful to the organizers who have made it fairly seamless to just beam in and join remotely. Hopefully next year the international travel will be less fraught and I can join in person. Okay, so as you all know, cold plasma dispersion leads to this characteristic lambda squared dispersion sweep, where the dispersion delay is a line of sight integral between us and the source. And just to spell this out really explicitly, the free electrons that are causing the dispersion of an FRB trace the baryons. Most baryons in the universe are ionized. We think most reside in dark matter halos and in between those halos in the intergalactic medium. And this gives us access to matter that's otherwise very, very difficult to observe directly, despite its outsized impact on things like precision cosmology systematics, galaxy formation, galaxy evolution, feedback, and so on. So this is a collapse quantity for a given line of sight, for a single line of sight, without importing external information. You don't know what fraction is coming from the Milky Way versus the IGM versus the intervening CGM or the host, and so on. Fortunately, for a large enough sample, each of these terms has a different probability distribution at a given redshift, and each of these has a different redshift dependence. So with a large sample, you can start to tease these apart. Now, a priori, the reason we don't know DM-IGM versus DM-CGM is because we don't know basic things like the fraction of the universe's baryons that are in the CGM versus the IGM. This is really central to the missing baryon problem. Some of you have seen this little animation before. This is just a line of sight simulated in IllustrisTNG. And what you'll notice is that DM doesn't increase linearly on spatial scales of megaparsecs. It's kind of a series of discrete jumps. And I've chosen an extreme sight line where we'll intersect a galaxy cluster. And in this case, the intracluster medium will dominate the total DM. But it's worth keeping in mind that usually you expect DM to be a series of discrete contributions from filaments and sheets and halos. I always like showing this slide. This is the final sentence of Dunk's 2007 paper, where they say if redshifts of their host galaxies are measurable, the potential of a population of radio bursts at cosmological distances to probe the ionized IGM is very exciting. Okay, so immediately they recognize that it's not just that FRBs are interesting by virtue of being cosmological and energetic and new, but they're also useful. So that paper was within 10 years of this famous Fukugita, Hogan, and Peebles paper in 1998, where they do a census of the low redshift baryons. And even when you're really stretching it, even when you make a bunch of assumptions about the plasma in groups, uh, you still come up short. In this case, you can account for maybe 40 or 50% of the baryons you expect. And this is really what I would call the classic missing baryon problem. The fact that 50% of ordinary matter in the universe is missing, is unaccounted for. And so the question asks, can we empirically determine omega b at redshift zero that agrees with the early universe measurements? Now, I'd like to propose a different framing where we kind of split it up into two different problems, the classic missing baryon problem, and then what you might call the strong baryon problem. And these are questions such as what is the exact spatial distribution of baryons? What is their power spectrum? What fraction are inside versus outside of halos? What is the relationship between that gas distribution and feedback, whether AGN or supernova feedback? What does a galaxy halo connection look like as a function of mass? And then, as Matt McQuinn pointed out on Monday, um, how do baryons at nonlinear scales impact precision cosmology experiments? I think this is probably our best chance, at least in the short term, of really impacting cosmology proper. So I would say since 2020, starting with the McCart relation, we have solved the classic missing baryon problem using FRBs. You sort of can't do it by other means because no matter how sensitive your X-ray telescope, you cannot image a void. And so the fact that FRBs are sensitive to all baryons means you really can account for the full omega B. We've started to chip away, take baby steps at the strong baryon problem. as I'll talk about later today. But really, I think the fun lies ahead. Oh, whoops. I think the fun lies ahead. The classic missing baryon problem is kind of amusing, kind of embarrassing, very important to address. But all of the messy, interesting astrophysics that come with the strong baryon problem are what we have ahead of us. Okay, let's dig a little bit more into the strong problem. So if you look at two simulations that have the exact same initial conditions, the same dark matter distribution, the same cosmology, and in this case, even the same collaboration, but you change the feedback prescription, you end up with very, very different gas distributions at redshift zero. So on the left is the original Illustris, on the right, IllustrisTNG. The original Illustris had very strong feedback. TNG has sort of strong feedback. And by redshift zero, the boxes are almost unrecognizable as the same volume. Okay. So distinct feedback prescriptions and star formation prescriptions lead to very different macroscopic gas distributions. So this is in addition to the fact that those baryons are extremely difficult to measure empirically. So it's not just that they're hard to observe, they're hard to simulate. Another way of looking at that is with gas fractions as a function of halo mass. So you can see that comparing five leading cosmological simulations, Eagle, Simba, Illustris, Bahamas. They sort of agree, they sort of converge at cluster scale halos, and that's because we're empirically constrained at those halo masses. Whereas below the group scale, you get these order one disagreements. Um, Viewed from a different angle, the power spectrum, you get these order one disagreements if you look at the total matter power spectrum, normalized by the dark matter only power spectrum. So you really distill the impact of baryons. If you plot that as a function of K, you can see again order one disagreements between the simulations. In most cases, you have some baryon suppression, meaning there are smaller matter fluctuations in baryons than there are in dark matter, likely due to feedback. And this is really important for these very expensive, very powerful upcoming weak lensing surveys. These are billion-dollar, billion-euro experiments where you want to measure cosmological parameters to a percent, and yet you have these order one disagreements about the nonlinear distribution of baryons, which make up 16% of the matter in the universe. So my understanding is that surveys like Dark Energy Survey currently just throw those modes out. They don't bother trying to model them or to marginalize over them. They just say, we don't know what they're doing, so we're just going to ignore them. Wouldn't it be great if we, the FRB community, could measure this power spectrum, hand it to the cosmologists, and allow them to really make these precision cosmology measurements that they set out to do in the first place? Okay, going back to the kind of intellectual history of dispersion and dispersion before FRBs, this is a paper that I somehow missed in 10 years of working on fast radio bursts, or maybe I knew about it and forgot. Harakon Sayama in 1965. This is the same Sayama of who supervised Stephen Hawking and Martin Rees and David Deutsch and all these people. The paper is called Proposal for the Detection of Dispersion in Radio Wave Propagation through Intergalactic Space. And the basic idea was, and keep in mind, this is 2 years before pulsars were discovered. This is about 2 years after Martin Schmidt got a redshift for a quasar. And they knew that quasars fluctuated. They were time variable. So they said maybe if there are short timescale fluctuations, you can actually measure dispersion from intergalactic gas. And they say you could measure this or else disprove these particular cosmological theories. They even have a little dispersion equation that you can see in the top right, although it took Steven Weinberg to correct this in his cosmology textbook. There's an error there somewhere. I also want to highlight that this paper is 1 page long. Okay. Here's another set of papers, dispersion before fast radio bursts. Here they were saying, well, we're going to have this extremely sensitive low frequency array, SK low. GRBs can come from high redshift, so maybe the radio afterglow will be dispersed by the ionized IgM if they come from sufficiently far away. So you can get a dispersion delay of 10 hours at 30 megahertz for an object at redshift 10. I also want to point out that at least the IOCA paper was 3.5 pages long. Okay. In the same category of prescient short papers, McQuinn 2014. So at this point, we know FRBs are real. We have the Thornton sample. And he basically lays out all the things that we are currently doing today. These bullet points are not summary points that I've made. These are just sentences from the abstract. So it says, DM is quite sensitive to whether the missing baryons lie around the virial radius of halos or further out, which is not easily constrained with other observational techniques. The intrinsic contribution to DM could complicate things. So this is the host DM, of course, it's a source of noise. And then stacking analyses of 100 DM measurements would place interesting constraints. And finally, scattering may result from turbulence in the CGM. Again, noting this is a 4.5-page paper. Um, I would point out that each of these bullets is now an active field of empirical science. These are, and in some cases, as you'll hear at the end of this talk and later in this session, with actual detections. Okay. Prochaska in 2018 shows us the expected dependence on impact parameter for halos of different mass when you intersect a halo along the line of sight. I also want to point out that it's not the case that FRBs are the only game in town, far from it. There are all these other methods that are much older than fast radio bursts that allow us to go after the hot ionized plasma in the universe. But it's a little bit like the parable of the blind man and the elephant, where one is feeling the tail and one is grabbing the leg and one is feeling the tusk, and you're trying to make sense of the whole elephant. Uh, Even though you're with X-ray, you're kind of mainly sensitive to hot, dense halo gas because of this NE squared dependence. UV absorption spectroscopy, you're measuring metals effectively in the CGM, but not the full content of baryons. TSE, KSE, again, mostly halos. And these are really powerful probes, and they're getting more powerful every day, as we heard on Monday. But it really takes FRBs to measure the whole elephant. This is a blessing and a curse, of course, because you can't disentangle the different components. But it's a really powerful tool. And this was what McCart did, okay, in 2020. This is measuring the whole elephant with just half a dozen fast radio bursts. So I want to emphasize that the scatter in this relation actually contains a lot of information about some of these questions in the kind of hard baryon problem. The missing baryon problem was, can we measure omega B? The hard baryon problem is, what is their distribution? So I want to just emphasize that there's a lot of information in 1-point statistics. I was skeptical maybe 3 or 4 years ago. But when you're at the kind of level where you don't know anything, even a 10 or a 20% measurement is useful. So let me just show a cartoon that some of you have seen before. But the basic idea here is, let's start with the trivial universe, where you have no large-scale structure, no filaments, no host galaxies. You have a one-to-one mapping in this universe between redshift and extragalactic dispersion measure. So the slope of that curve goes like omega b times h naught times the fraction of baryons in the universe that are ionized. If we throw in intervening galaxies and assume that these halos are full of hot ionized gas, then you've injected some scatter, but because we have this cartoonishly smooth background IGM, you have a lower limit for how much DM you get for a given redshift. You have noise on top of that, which comes from the Poissonian intersection or non-intersection of intervening halos, but you always have this kind of minimum DM for a given redshift. If instead most of the DM were coming from the host, as we proposed very early on, then there should be no McCart relation at all, or it should be washed out heavily. If we have a more realistic universe like TNG 300, where you have reasonably strong feedback, you're kind of sloshing gas around. You have this homogenization process from the feedback, and you still end up with a kind of statistical minimum for how much DM you get along a given line of sight, because even if you miss all the halos, you still get a fair bit from the IGM. So in this scenario, about 4/5 of the universe's baryons reside in the IGM, and you have this pronounced DM cliff. If we have a baryon distribution that more resembles the dark matter distribution, where about half of the total matter is in halos, then we have a puffier distribution. There's more line of sight variance. It's a clumpier universe. You still have a DM cliff, but it's at a lower angle. It's a lower slope, as you can see, going back and forth. The way I think of this is kind of walking through a misty rain versus walking through a hailstorm. So when you walk through a misty rain, you always get pretty wet. And you get about as wet as far you walk, right? If you walk twice as far, you get twice as wet. Walking through a hailstorm is very high variance. You can get lucky and miss all of them, or you can get unlucky and hit a really big one. And that's the kind of scatter that you get in the scenario where most of the baryons are trapped in halos. This is shown explicitly by Kriti Sharma in a recent paper where she shows the relationship between these kind of McCart plots, these one-point statistics, and two-point statistics like the baryon power spectrum. So on the left, weaker feedback, like in Astrid, you get a lot of line of sight variance. There's more gas and halos. On the right, you have stronger feedback, like in Simba, where you have a more smooth universe, less line of sight variance, a steeper DM cliff. Okay, so what do we actually see? We now have of order 100 localizations, so we can start to test some of these ideas. If we extend the axes of the McCart plot, we get something like this. And if we plot over the sample as of, I think, January 2024, so already quite out of date. But you'll start to notice a couple things. The first is that we now have a high redshift sample. So we have FRBs going beyond Redshift 1, indeed beyond Redshift 2, which is extremely exciting. Didn't have time to remake this plot, nor should I have, I guess. But we also have low redshift FRBs spanning a total luminosity function or luminosity distance of 220. The other thing you'll notice is this unmistakable DM cliff. So there's nothing in our sample at that time below DM of 800 times redshift, which is remarkable. Like a priori, you did not know that it would be really hard to produce a redshift 0.6 FRB with a DM of 300. The universe could have been that way. But there seems to be this really pronounced cliff, which tells us that the baryon cosmic web is relatively smooth. At least some of the gas is outside or is expelled from halos, at least compared to the dark matter distribution. And when we fit a model to this, we find that 3/4 or 4/5 of the universe's baryons are in the IGM and outside of halos. So this is significantly larger than the fraction you'd expect if there were no feedback, where FIGM should be about half, roughly. So this indicates efficient feedback processes that can expel material or prevent gas from falling in the first place, uh, which is in line with other measurements. So just to go back to this toy example, which is actually maximally conservative, this example where 50% of the gas in the IGM and the IGM is perfectly smooth, that first cartoon that I showed you, you would have a DM cliff at roughly this angle, and just to overplot what we see, it's quite different. Okay, so if we import information from these other probes like X-ray, the eROSITA cluster catalog, group and cluster catalog has 10 to the 4 objects. We now have thousands of SC groups and clusters. And so we can go beyond just saying IGM versus non-IGM, halos versus IGM, and actually partition the baryons into a complete baryon pie chart that looks like this. And this is in comparison with the state of affairs 10 to 15 years ago. This is from Mike Shull's paper. And there I'm including the baryons that could be directly measured, directly constrained. So now we've not only measured omega B, but we can actually partition the baryons into these different components. And what we see is in agreement with cosmological simulation. So if you turn off all feedback in Simba, FIGM drops down to below 60%. Whereas if you have all the AGN feedback and everything turned on, FIGM is north of 80%. And we're seeing a similar story from these other probes. So a recent cross correlation between KSC and Photo Z Galaxies, I think Legacy, showed baryon deficient halos. I'm less inclined to try to interpret the X-ray data because it's so out of my wheelhouse. But my understanding is that the X-ray stacks also indicate baryon deficient CGM.
You've got 5 minutes.
Thank you. Okay, I might try to whiz through this real quickly, but um, these hints of strong feedback and large FIGM may help with the S8 tension in cosmology. Just this basic idea of smoothing out the matter distribution. This tension comes from a disagreement between the inferred matter fluctuation amplitude from the CMB and what one actually measures with weak lensing. And I think you can do this without any new physics or breaking cosmology. You just have strong feedback and slosh the baryons around. We get a 10% measurement of omega B H70. It's hard to do better than this actually, because the early universe measurements are measuring omega B H70 squared. So you've got this H naught factor. So you can't do much better than 10%. Everything I just mentioned was totally agnostic about the foreground galaxies. And obviously, there's a lot of information in the large scale structure that we can observe between us and the source. So Flim Flam is very maximalist about this. Flim does these heroic spectroscopic galaxy surveys in the direction of fast radio bursts, and this allows them to do a full 3D reconstruction of the cosmic web towards those sources, and then use that as a prior on what you expect from the IGM component, the halos, and so on. Another method that you'll hear about in a few talks is by my student Maryam Hussaini, where she's found one of the first detections of the large-scale structure using fast radio burst DMs. Her results seem to imply most of this is coming from scales much larger than halos, so likely from the IGM, not from the individual CGM of intervening galaxies. And we'll also hear tomorrow a very exciting result from Kiyo Masui's group. Hao Chen is going to tell us about the first detection in cross-correlation between unlocalized fast radio bursts in CHIME Catalog 2 and DESI Legacy Survey, the BGS sample specifically. So in the past 5 weeks or something, we've had the first detections of the large-scale structure with FRB DMs. These are the baby steps I was talking about before. And these will only grow more powerful with time, especially as we have more redshifts and we're able to subtract off the largest source of noise, which is the McCart DM. In the future, when we have many thousands or tens of thousands of FRBs, we want to move into a large-scale cross-correlation game. The most obvious one is spectroscopic galaxy survey or some billions of photo-Zs from Rubin, let's say, cross-correlated against delta DM, so excess dispersion measure after subtracting off the McCart DM. And this will give us a cross-power spectrum that contains a lot of information about feedback and galaxy formation and can also maybe help with this KSC tomography degeneracy. Another nice idea that Calvin Leung and Robert Reischke have proposed independently is cross-correlating weak lensing shear maps with FRB DMs. The idea here is that weak lensing is sensitive to all matter, dark matter, and baryons. The dispersion measures are sensitive only to baryons, and so you can kind of disentangle the contribution from feedback and from baryons. Here's a nice cartoon example from Robert, where he just shows what you get from Euclid in constraining the matter power spectrum with and without 10,000 fast radio bursts. And the point here is just that you can actually figure out what the feedback scenario is with the FRBs and allow Euclid's incredible statistical power to be used for the cosmological parameters that it actually cares about rather than just constraining feedback. And we will have samples like this in coming years, thanks to CHORD and SKA, DSA 2000. I would point out DSA 2000, if it's able to search the full field of view with effectively all baselines, could see something like 25,000 per year. This is a compute question. We expect to get localizations of 100 to maybe 300 milliarc seconds, thanks to the oversampling, the very good UV coverage, and an excellent PSF. The scary thing about having as much sensitivity as DSA 2000 and CHORD and the square kilometer array is that we're going to find a lot of FRBs from really, really distant galaxies. So obviously we don't know if the universe produces reionization FRBs, but it's worth noting that half of the DSA 110 sample would have been detectable at Redshift 6 by the DSA 2000. So if such objects exist, we will find them, and this will give us a column to reionization. On the other end of the spectrum, there are these upcoming all-sky monitors, these enormous field of view aperture arrays that can see thousands or 10,000 square degrees continuously. These will find local universe events. Of course, the one that's trailblazing is BURST, but there's also CHARTS, which will be built in Chile. We are building the coherent all-sky monitor, or CHASM, at OVRO, hopefully with the first on-sky data later this summer or early this fall. There's a cosmic antenna in China. And this is really nice because you end up in a scenario where you could find hundreds of FRBs within a few hundred megaparsecs. So when everything is coming from Redshift 0.4, follow-up is really hard. You kind of have no chance of detecting coincident X-ray emission or fast optical. And then also going after the CGM is hard because, as we've shown, it's really the IGM that's doing all the dispersion. However, if we had a local universe sample, the IGM doesn't contribute much. So we go from this scenario to this scenario, where really you just need to reliably subtract off the Milky Way's ISM, try to model somehow the host galaxy's ISM, and then you have this joint measurement of the Milky Way's halo and the host galaxy CGM, which is a really clean way of going after the baryon content of Milky Way-like galaxies, circumgalactic media. You may remember this paper by Vikram Rabi a couple of years ago where we found a local universe FRB 50 megaparsecs away whose total DM was lower than the value predicted by both NE 2001 and YMW. You'll hear more in the next talk from Ralf Konietzka, my student, about his amazing simulation work. This just shows what the sky might look like out to redshift 0.05, I think. So to wrap up, I know I'm a little bit over time. We've more or less solved the classic missing baryon problem using FRBs. And we've begun to take baby steps towards the hard baryon problem. So showing that FIGM is large, requires feedback, maybe suppression in halos from Hao Chen's work. We'll soon have huge numbers of FRBs, and where cross correlation with other cosmological fields will be the name of the game. And I would just make a call that it's not just that we need 1,000 or 10,000 FRBs. We also need new theory, algorithms, simulations, and more expertise in non-FRB fields, in galaxy formation, KSC, and so on. This is happening, and it's led by mostly young people, Medlock, Sharma, Konietzka. But this work is really important. If you gave us 10,000 localized FRBs tomorrow, I don't think we could make much sense of it right away. We'll soon have a way of measuring the Milky Way CGM and host galaxy CGM. And with that, I'm more than happy to take questions.
Okay, we have time for a couple of questions. You're next.
Hi, Liam. Thanks for the nice talk. It's Ilya in the process. I'm Ilya Hagen from Catholic University, Valparaiso, Chile. How does your constraint on FIGM and FCGM fractions change if you correlate your observed DMs with different simulations and not Illustris?
Yeah, this is a really good question. I mean, I showed Simba where you actually turn off fully all feedback and turn on different strengths of feedback. And you end up with distributions that we roughly expect. I mean, what we really need to do is do this in a simulation suite where you can turn all the knobs that you care about, where the volume is large enough that you can trust the cosmology. So something like CAMELS 50 or Flamingo. But to answer your question more directly, we haven't done the experiment of turning all those knobs. But I would just highlight that we have P of DM given Z for different simulations with different feedback strengths. And I think our data sit in between TNG and SIMPA.
Hi, Liam. This is Rachel Darlinger from McGill. I was just wondering, you showed two scenarios with a DM cliff. How do you distinguish the DM cliff for the IGM and CGM so that you preferred one over the other?
Yeah, so I guess the point here is that when all the gas is in the CGM, you don't have much of a DM cliff, or at least it's at a very low slope. And that's because the DM cliff really comes from the fact that when you go through the IGM, you're guaranteed a lot of gas contribution because you're guaranteed to intersect 100 filaments and voids and sheets and everything. Whereas halos are small and they're easy to miss.
Great. Oh, there's an online question. Do you want to, Sunil?
Thank you. This is Sunil from U Chicago Northwestern. Liam, great talk. So I guess this question goes back to the discussion session we had earlier during the conference, and in the use of photometric redshifts for the FRB hosts themselves. So I was wondering if you have a sense of how much better or how much worse we would be doing in, like, say, retrieving baryonic information from the McCart plot if we were to use photometric redshifts instead of spectroscopic ones. So I don't know if you had looked into that.
Yeah, I don't have a lot of intuition for this. I think if you're using photo Z's that are as good as legacy, in this stage we're at now where 10% measurements matter a lot, like 10% measurements are good, legacy photo Z's would probably be just fine, honestly. Um, that will maybe not be true in the future, but it's absolutely a question we can forward model and should do quickly. I mean, soon we will have all 50 million or 40 million spectroscopic redshifts from DESI, 10,000 FRBs, and of order a billion photoz's. And so we need to figure out what to do with those data, basically.
Got it. Thank you.
Great. We'll do one more question from Lordrick online, and then we'll go on to the next talk.
Oh, thank you. I'm Lodrick from UCSC. I feel like you answered half my question probably, but I was just wondering if we could.
Lordrick, I think your microphone's too far away because we can't hear you.
Okay, maybe I'll ask my question on Slack.
Oh, you came back just now. If it's a quick question, go for it.
Oh, okay. Yeah, so I was just wondering, so in terms of, I know how is a small payload small and easy to miss, but
unfortunately, you faded out. So I am going to ask you to ask the question on Slack instead. And Liam, please look at Slack for that question.
Sure.
I apologize, Alodric, but I think the audio was too challenging there. Great. Let's move on to better understand how simulations are modeling our dispersion measure versus redshift. And so, Ralf, I'll let you take it away here.
Hello, can you hear me? Is the audio okay?
Perfect.
And can you also see me? I can't see myself, so I'm not sure if you can see me.
We see you and we hear you.
Okay, perfect.
Oh, sorry. We don't see your slides. We only see you.
Now you should see the slides as well.
Now we see the slides. Perfect.
Okay, perfect.
And we still. Thanks, Gil. That's why we have you on the team.
Okay, am I good to go from your end?
Yep.
Okay, perfect. Hello, everyone. My name is Ralf Konietzka. I'm a PhD student at Harvard working with Lars Enquist and Liam Connor. And today I will be focusing on everything what happens between the origin of the fast radio burst and the Milky Way, meaning how is the cosmic web affecting the fast radio burst signal. And to this end, we will be using the IllustrisTNG simulation suite, which simulates a box of the universe, a box of the cosmic web between the burst and us. And my talk will be structured as follows. I will first go through the methodology on how we can model fast radio bursts within IllustrisTNG. From there, I will show how we can draw several different catalogs based on our technique, which then allows us to apply those catalogs to, for example, determine analytically the shape of the dispersion measure distribution function. So let's dive into the methodology. We have here a single simulation box of IllustrisTNG, and what we would like to do is we would like to send rays through this box and then accumulate the electron density to get a measure of the dispersion measure. And once we have done so, and I will describe the details of doing that in detail soon, is we want to extend our measurement of a single box to several boxes to go to deeper and deeper redshift. Keep in mind that one single simulation box in the biggest TNG volume has a length of roughly 300 megaparsecs, while we want to go with a redshift of over 5 to more than 5,000 megaparsecs. So let's start with a single box first. And here we have to keep in mind that IllustrisTNG is run on a Voronoi tessellation. So there's no Cartesian grid underlying the simulation, but this Voronoi grid. And if you want to know how much electrons were accumulated from the start to the endpoint here in shown in blue, we have to reconstruct all the line segments that were crossed within this Voronoi tessellation. And we develop an algorithm that does this on the fly, and I will outline the algorithm shortly. We first find for each cell, for the start and for the end cell, its cell generating point or its center, and construct this orange ray between the cell generating points. Then we can split the orange ray in half by a plane entitled E in blue. And if the blue cells were attached by construction of the Voronoi tessellation, the plane E would be the boundary plane between those two cells. But as the cells are not attached, the plane E gives us a new cell where we can identify a new cell center or mesh generating point shown in orange, and we can identify two new orange lines from where we repeat the algorithm recursively, finding new two blue planes that, as the cells are still not attached, give us two new cells, and we again continue. Now we are in the scenario where two cells are attached, here, for example, in the right. And by construction of the method, the blue plane is exactly the boundary plane between those two cells, and the algorithm stops here. Well, in this part of the algorithm, we have to go one step further to now find the last cell, and now we have reconstructed the entire Voronoi cell tessellation, the sense that we got all the line segments that our ray crossed. So we have a good understanding how we can get rays for single simulation box, and now we want to extend this to higher redshifts. So we need further more boxes. And the way we implement this in our method is the so-called continuous ray tracing approach. So we present this method where we trace rays under an angle through the simulation boxes. And here it's important to note that all the boxes have periodic boundary conditions, meaning that if you leave the box here, you enter in the same position in the next box. If you would trace the rays parallel to those boxes, you would go through the same structures over and over again. And to avoid this, we use tilted rays that then go over and over almost until infinity without crossing the same structures twice. And this algorithm is especially great because there are no gaps between the snapshots. And with this method, we address a problem in previous IllustrisTNG based approaches where the integration of the path integral was based on the trapezoidal rule. And this method introduced gaps between these different simulation volumes, which then lead to this torsion of the final dispersion measure distribution. You can adjust the mean of the distribution with this method, but not any of the higher moments. And I will now compare our blue continuous ground truth approach with the current approach from the literature, and we see across all redshifts, the trapezoidal approach heavily distorts the distribution, especially when we go to higher redshifts. And to analyze this not only in the distributional sense versus dispersion measure, but in the sense of the moments of the distributions, you see, as I already said, the mean is the same for both methods. The trapezoidal method basically accounts for the mean correctly, but any other higher moment, especially the standard deviation, gets changed by up to more than 50%. So it's really important to use an accurate methodology such that the width of the distribution is modeled accurately. And now having this implemented, we have a perfect methodology to now draw catalogs from IllustrisTNG. And the advantage of this methodology is that we can trace rays with our continuous approach that reconstructs the Voronoi tessellation. We can trace rays on all angles of the sky, meaning that we can produce catalogs in the form of full sky catalogs. And I'm showing here our main full sky map integrated up to Redshift 0.01. And you see how the voids in black are transversed by blue filaments and red halos. And it's especially important to note here that while the most fraction of the sigma arises from the filaments, the highest DM peaks occur within the halos that are highlighted here in red. And we can even zoom in using our pencil beam catalog in one of a patch of the sky essentially to see how the CGM around certain halos looks like in further detail. And if we now want to see how the structure was accumulated over distance or go even deeper in Redshift, we can run our approach continuously and then see there's more and more dispersion measure accumulate. We see the foreground structure, the small modes fill up, and the higher we go in distance, the more the larger modes get accumulated until we almost see a fully blue sky in terms of dispersion measure at roughly redshift 0.5 and higher until we reach our final redshift of around redshift 1.3. And while we in all those runs so far have chosen one specific position of the observer, we can also rerun our approach with different observer positions where we locate ourselves always in Milky Way-like environments. So those are 4 different runs with 4 different start points of the observer. And we always make sure that we have a Virgo-like halo at roughly 16 to 17 megaparsecs from this Milky Way-like galaxy, as well as an Andromeda-like galaxy in the vicinity of the halo that we use as the observer. The Andromeda-like galaxies are roughly a megaparsecs away. And we see again wonderfully how the different environments give different snapshots of our local universe. And we can also trace those maps deeper in Redshift to learn how the large scale and small scale fluctuations change when we go to different Redshift slices.
You have 2 minutes left.
Thank you. All of these methods will be made publicly available. You can access them on this handy web page. And now, finishing the catalog section up, I would like to show shortly one application of our methodology and of these catalogs, namely what we can newly learn about the dispersion measure distribution function. In 2020, McQuad introduced this normal power distribution, which is mainly a function of only the standard deviation, where the mean is intrinsically fixed by this X0 parameter. And based off that, Walker and Sharma in 2024 and 25 argue that maybe log normal distribution is a little bit better. And we now introduce a third approach showing them the so-called normal power 3-1 distribution, which is very similar to the McQuad form, but we leave this mu parameter, which is for high redshifts, equal to the mean free and also change the slopes of the distribution. And with our ray tracing technique, we have now the tools to compare those distributions to each other to figure out which of them fits the best. And we apply an ensemble of distributions shown here in these other colors that I'm not talking about today. The main point is our proposed normal power distribution function gives a perfect match to the data, while the log normal and the distribution suggested by McQuad are both not ideally matched to the data. They both are not able to properly constrain the high DM tail as well as the low DM tail. And this image is now shown at redshift 0.5. Even if you go to other redshifts, our normal power function, here shown in blue again, gives overall the lowest Kolmogorov-Smirnov statistics, which means it's the closest fit even across redshifts. So we've now found a distribution that only has 2 free parameters and those general global shape parameters that fits the distribution function perfectly nicely across all redshifts and improves upon the earlier announced distribution functions. And with that, I want to wrap up saying, I have now introduced you this methodology of we can correctly ray trace rays through the IllustrisTNG suites. We constructed several color logs from there and applied those color logs to a first problem or first analytical description of the distribution function. And with that, I'm happy to take questions. And if you would like to download and use the catalogs, feel free to access this QR code where you will also find a Jupyter notebook that shows you how to plot the data, open the data, and also how to basically work with this new distribution function model that we proposed as an analytical description for the DDM distribution. Thank you.
Great, thanks, Ralf. Let's move directly to an online question from Isabel. Isabel, do you want to go ahead and unmute?
Yeah, hi, Ralf. Great talk and congratulations on the new paper. I had a question about your new proposed distribution. Do you have a physical motivation or an idea why the alpha equals 1 and beta 3.3 works better than the previous McQuart relation or the Kriti Sharma's
Yes.
law?
Let me share my presentation again. Can you see my slides?
Yes.
Perfect.
Yeah.
So this new distribution accounts for the fact that the distribution function really wants a power law cutoff on the high DM end, which is not included in the log normal functional form, where it goes basically sharply down with an exponential decrease. And on the other hand, on the low DM side, you want to have an exponential rise that's not too strong. And the McQuad rise here was a little bit too strong with this alpha parameter equal to 3. You want a little bit a shallower rise. And the reason then why a power law is a very nice fit, there's this idea that the the high DM end is many dominated, as already showed from the full sky maps, by the halo part. So basically, the distribution function of the halos tells you how the high DM part looks like, and then also informs you how the shape parameter beta has to look like. While on the low DM end, it's mainly the filaments on the voids which shape the functional form, and then the form has to become more and more normal distributed, as shown in this figure here. So at redshift around 4 to 5, it's almost a perfect Gauss distribution.
Okay, thank you.
Great. Any questions in the room here?
Hello, this is Dylan Zhao from Stanford. Just looking at some of your diagrams by eye, even using this sort of tilted ray tracing trajectory through the repeated boxes, it kind of looked by eye that you would still, for the larger scale structures, kind of be overcounting these and hitting them more than once. So this may be just a function of how the diagrams looked, and it may not actually be a problem. So is this a problem that you have to worry about, and how do you deal with that?
That's a very good question. This was one of the core analysis parts of this work. It's not a problem, and we've checked for this with several different approaches. It's a matter of choice how you choose this ray, but if you choose this correctly, you can get along with that. And I'm showing here other approaches where you break those correlations that were introduced by the continuous approach using this so-called stacked ray tracing approach, where you also rotate and shift the boxes, and those two approaches are consistent with each other. And we also tested what happens if you look in different directions on the sky, how these repetitions are imprinted, and we see that for more than 97% of all the directions on the sky, this effect does not matter. There's a slight bias, which you get around of that if you use plane parallel arrays, but even for the full sky catalog, up to not more than 2%, this is not a problem. Thank you for the question.
Great. Thanks, Ralf. Sunil, I do see your hand, but I'm going to ask you to ask the question in Slack, and we'll move on to the next talk. Isabel, do you want to unmute and share your screen?
Can you hear my voice and see the screen? The slides.
We hear your voice, see the screen, and we see you.
Okay, great. Thank you.
Is that correct, Yo?
All right. Hi, everyone. My name is Isa Medlock. I am now a rising fifth-year PhD student at Yale, working with Daisuke Nagai and the CAMELS collaboration. And I'm going to speak a bit about some of my previous work for the first half, and the second half is something that's more of a work in progress / a proposal. So to motivate everything is baryonic effects on cosmology and astrophysics. We all know that baryons have complex and wide-ranging effects on the physics of the universe, as many have talked about earlier, including on the baryon cycle and the circumgalactic medium, where all these processes such as outflows, accretion, recycling gas, and so on, are all shifting and moving baryons in the CGM. And then on larger scales, we have the larger scale structure. And if we look at, for example, the matter-power spectrum, we see that baryons change the way the matter-power spectrum behaves in relation to if we only had dark matter. And these predictions of how baryons affect both the matter-power spectrum as well as the CGM gas distribution are hard to model. And even with simulations, they vary significantly depending on what subgrid models we choose to implement. So this video is from the CAMELS collaboration, and it's showing an example for 8 different subgrid models. In blue is the gas density, red is the gas temperature. As it evolves through redshift, just how significant these differences can be. And we call or usually refer to these simulations like Simba or Obsidian in the lower right, where the gas is being expelled much further as having stronger feedback than something like Astrid or even TNG in this case, which is a bit more tame compared to Simba and Obsidian as having weaker feedback. So this is a really complicated issue, and we can't really directly observe the CGM and these effects because of how diffuse the gas is. So we really need nice probes. There are other probes like KSC and TSZ, X-ray, and so on, but each of those has their own caveat. And that's why something like FRBs is so exciting, something that is directly tracing the ionized baryons along their line of sight. And as people have shown before, from the host of the FRB to us, the FRB is picking up signal from everything in between, and that includes the DM host galaxy, contributions from the Milky Way, ISM, and CGM itself, but then also things in between, like intervening galaxies and halos, as well as the IGM, voids, filaments, sheets, and so on. So we get this number that encodes a lot of information. And as the video previously illustrated, depending on what simulation you use to make your predictions, you're going to get wildly different predictions. So this is why I've been using the CAMELS project. And the goal of the CAMELS project is to collect these sets of now tens of thousands of simulations, along with n-body simulations with different subgrid models. And these are all run with the same initial conditions, the same resolution, the same box size, in order to get them as close as possible and really be able to directly compare the effects of the subgrid models themselves. And in addition to just varying the subgrid models, within each subgrid model, they vary different parameters, including omega matter and other cosmological parameters, and then feedback parameters that describe, for example, the strength of supernova feedback or AGN feedback. And this results in a huge number, again, over 14,000 different simulations, each have slightly different physics. So you have this huge parameter space that we can look at. And in my prior work up till now, I've looked at the CAMELS simulations, specifically the first three that were available, TNG, Simba, and Astrid. And one thing I looked at was on the scale of the CGM, what do excess dispersion measure profiles look like as a function of impact parameter? And from that, we saw that initially we can see a pretty clear and distinct difference between what we see in a simulation with weaker feedback, such as Astrid, where we have these really boosted DM excess profiles, versus a model like Simba that has such extreme AGN feedback and really ends up pushing so many of the baryons out of the halo. We see these really suppressed dispersion measure profiles. And that, in general, was just indicating to us that FRBs are a really promising probe to be able to test the proximity to these different feedback models on the CGM scale. Another thing I worked on more recently was looking at the F parameter, or basically the spread at a given redshift in the McQuart relationship. And one thing we showed was that this F parameter pretty tightly correlated with the suppression in the matter power spectrum due to baryons with respect to if the matter power spectrum was only dark matter. That's really exciting. I think it's more of a proof of concept that FRBs are a powerful approach to potentially doing this in the future. And recently, Kriti Sharma put out a paper with the new proposal for the log normal parameterization and a more in-depth look at the matter power spectrum suppression, which is really nice. So I think this is a really promising forward approach. But there's a big caveat to the work I've done so far, and then in general, any work that involves CAMELS. There's several, but the main one I want to focus on is the box size. CAMELS is a 25 megaparsec box size, which is way too small to properly capture cosmic variance in all the width of structures in the universe. So it's not something that we can use to actually apply to observational data. So this figure from Batten et al. 2021 really shows that you need a certain box size, I think at least 50 megaparsecs, but ideally more, to converge in the variance in DM, which is what you would need to properly measure something like the F parameter or whatever other statistic you want to use. So something that we've been working on is thinking of ways that ideally what we would want is a large number of really large cosmological boxes with, similar to CAMELS, many different variations on cosmology and feedback, without having to deal with the fact that cosmological simulations are extremely computationally expensive and time-consuming. So I'm a member of the Baryon pasting project, which is led by my advisor, Daisuke Nagai. The Baryon pasting project's goal is to develop a simple physically motivated, computationally efficient analytic method for modeling baryons that is calibrated on both existing observations and hydrodynamical simulations. And what that means is that you would have an input of a dark matter only simulation, which is so much cheaper to run than a hydro simulation. And then based on the analytical model, which starts first from the center with gas in hydrostatic equilibrium with dark matter potential, and then adding different gas physics, it's a growing model. You can paste on where the gas would go and end up with a volume that contains both dark matter and baryons, which is much cheaper to get. And then from that, we can make predictable observations. And this has already been used successfully to create large-scale maps of the KSC and TSC effects. And there are two main methods for this. Sorry?
You've got 2 minutes left.
Okay, thanks. There are two main methods that baryon pasting is done. A halo-based pasting, where we just have a model of how gas is distributed around halos and paste that on top. And here are examples for the TSC and KSC effect. And that one's very quick and works well for TSC. And then a more expensive model, which considers all particles in the field, including anything outside the halos, and that's pretty slow. And it works better for something like KSC, which is sensitive to the diffuse gas beyond halos, but that's still pretty expensive. FRBs, as many people have already talked about, including Ralf, depend significantly on the IGM. The number we get is very a large number comes from the IGM. So if we want to do something like baryon pasting for FRB observables, we need to have a good handle on what filaments in the IGM are contributing. So something that I've been working on in the last few months is developing a joint halo and filament model for baryon pasting to efficiently make simulated FRB maps, specifically working on a model for the filaments. Right now, we have two starter models, an isothermal model to model filaments, and another model that is based on halo self-similar collapse, but this is self-similar cylindrical collapse to describe filament profiles. And main work in progress right now is with Daniela Galarraga Espinosa, who is an expert on cosmic filaments in simulations, and we're working on refining the model and comparing to that to really bring it together. But basically, our main goal is to just develop the strong, robust model that we can then apply to thousands of different n-body simulations with different cosmology and different feedback physics to end up with many, many volumes of data that we can then use for FRB maps in combination with other observables. I think I'll end there with my conclusion slides. Thank you.
Okay, questions for Isabel? Rachel.
Hi, Isabel. Thank you for the talk. This is Rachel from McGill. I was just wondering if the pasting of the baryons affects the simulation based on how it could evolve to that point, or if it still works well.
Sorry, I didn't quite understand the question. So you're asking if the pasting impacts the evolution of the simulation following that?
Or the accuracy of the model based on the pasting in places where it hasn't evolved there?
The model it's applied at a given redshift snapshot, and the model has a redshift evolution as well to take into account for that. I'm not sure if that quite answers your question. But...
Yes, thank you.
Any other questions here in the room? Online? Calvin's got a question.
Hey, Isabel. Calvin here from UC Berkeley. Do you think that the n-body simulations, such as those that you're working on right now, or large-scale hydro, such as we heard from Ralf and Liam, are the way to go into the future for cosmological and baryon inference?
Yes, so I guess this project is not just intended for FRB purposes, although that's what I'm interested in primarily, but I think it's also just a way we're thinking of being able to generate more efficiently than having to run hydro simulations. Many models that could then also be run for inference and machine learning applications, and not just for FRBs, for other observables. Like it's already been done for TSC and KISC and so on.
Great. We'll take one more question online from Kriti. While she's asking, Shion, do you want to go ahead and set up?
Hi, thanks Isabel for your amazing talk. I just wanted to ask, so I think one of the other caveats of CAMELS that I can think of is that it does not fix other observables while varying feedback. For example, the stellar mass function or say galaxy star forming main sequence, which are already very well understood. So is there a way to include that in ongoing or upcoming CAMELS projects, or for example, in your Baryon pasting algorithms?
So from the CAMELS project, from what I understand, their goal isn't exactly that every simulation or every volume is actually realistic. They're just going for like the most extreme range possible to look at all that. But I do think you're right that it's important that the volumes or the information we actually use is able to match observables that are well known. But I think we haven't fully thought about how exactly we're going to do that yet. But that's a good point. Thank you.
Thanks.
Great. Let's thank Isabel again. And the next speaker is Shion Andrew, and she's going to tell us about selection functions for the Outriggers.
It's fine.
Yeah. Should fit under your ears.
Wait. Can everyone hear me? I think so. Is it on? Louder? Okay. Can everyone hear me now? Yeah.
Louder.
Okay. How about now? Okay. Sorry about that. So my name is Shion Andrew. I'm a PhD student at MIT. And today I will be talking about the importance of selection effects in large-scale structure studies and how that relates to CHIME and CHIME FRB outriggers. All right, so what we want to do with FRB DMs is we want to use these DMs to tell us about the spatial distribution of electrons in our universe. And as has already been mentioned today, one way that we can quantify this is with the electron power spectrum measurement, which just tells us how much electrons are clustering on different spatial scales. And here is a comparison between Illustris and IllustrisTNG. And as Liam has already said, these two simulations are more or less identical, except they model feedback differently. And based on these electron power spectra, you can imagine making this measurement to constrain different models of astrophysical feedback using whatever combination of hydrodynamical simulations that you want. So unfortunately, we don't have an infinite number of FRBs at an infinite number of redshifts. And even though in the near future, like as in the next decade, we might have thousands to maybe even tens of thousands of FRBs with redshifts, we won't have the millions to billions that are needed to reconstruct this underlying electron map with high fidelity. So when it comes to doing two-point statistics, we really have a sparse reconstruction problem. But one thing that you can do is you can cross-correlate your FRB DMs with another tracer of matter for which there's an abundance of measurements. And that gives you a boost in your signal to noise. And that is really one of the main motivations for cross-correlating FRB DMs with foreground galaxies. And now the power spectrum measurement you get is an electron galaxy power spectrum measurement, which tells you about the relative spatial distribution of electrons and galaxies, which you can still use to constrain feedback. All right, and finally, because the DM is an integral of the electron density along the line of sight, what we really measure with real data is an angular cross-correlation, which is just an integral of the electron power spectrum over redshift. But it turns out that if you have redshifts for your FRBs and you choose to cross-correlate your FRBs with galaxies that are strictly in the foreground, you can measure this electron galaxy power spectrum measurement directly. And intuitively, this is just because only the component of the electron density that's co-located with that foreground galaxy will actually correlate with those galaxies. So you kind of extract that electron galaxy power spectrum slice for free. And it's really worth stressing that this is why we want to do this kind of measurement specifically with a large sample of FRBs that have redshifts. Because if you don't have redshifts, you can't enforce the condition that your FRBs are strictly in the background of the galaxies you're cross-correlating with, in which case you can't get the electron galaxy power spectrum measurement unless you model your FRB distribution in some kind of way, but that inevitably introduces error into your measurement. And then, as Liam said, the other big reason why FRB redshifts are nice is because you can remove this distance DM over density degeneracy by just subtracting off the Makar relation. Okay, so there's already been variations of this galaxy DM cross-correlation measurement done in the literature with real data. So for example, Hao Chen has a 5 sigma detection with 3,000 FRBs from CHIME catalog 2, although those don't have redshifts. And right now, the number of FRBs that do not have redshifts far exceed the number of FRBs that have redshifts by about an order or 2 in magnitude. But even with just 60 host localized FRBs, there's been a 3 sigma detection with a galaxy stacking analysis. And I think Maryam's going to talk about that later today. So there's really a lot of power in these FRBs that have redshifts. And in the near future, we're going to have many, many more redshifts with CHIME FRB Outriggers coming online, as well as many other next generation telescopes. So, an era where we can make this galaxy DM cross-correlation measurement with more and more precision is truly imminent. But of course, it doesn't matter how many FRBs we have if there are unaccounted for selection effects that significantly bias the measurement. So for an Outriggers localized sample of FRBs that also have redshifts, there's multiple levels at which selection effects can be introduced. So there's the CHIME detection system itself. This is modeled with hundreds of thousands of injections. Kyle talked about this on Tuesday. There's also the fact that we only Outrigger localize a subset of all of CHIME detections. And of that subset, only a subset of that subset actually gets a redshift measurement because of optical selection effects. So when it comes to this specific measurement of cross-correlating FRB DMs with foreground galaxies, it turns out it's useful to think about our selection effects spatially. So that's to say it's useful to think about selection effects that are that arise due to observables that are local to the FRB itself and its host galaxy, and selection effects on observables that arise kind of along the line of sight. So when I say FRB local, I'm referring to selection effects like optical selection effects on the host galaxy itself. So how bright is the host galaxy? How large is the host galaxy? This also includes the DM or the host contribution to the total DM and the host contribution to the scattering measurement, as well as many different burst properties like the intrinsic burst width, the spectral index, etc. But those observables are not expected to correlate with the foreground galaxies. So the expectation is that those FRB local selection effects will not bias the measurement. But what can bias the measurement are selection effects that arise within the galaxy foreground redshift shell. So this includes DM-dependent selection effects. So for example, if you have a DM-dependent selection effect that makes you unable to detect FRBs beyond, say, 300, you can imagine missing sightlines that are tracing a really large electron over-densities near your galaxies that you're cross-correlating with, in which case you would underestimate the extent to which galaxies are correlated with electrons. And this also includes observables that may be correlated specifically with the DM over densities within that galaxy foreground shell, like scattering if you're observing your FRBs at a high enough redshift. Okay, so we can test the effect of these selection biases using ray tracing simulations. And this was work that was done by April Cheng, who's a PhD student right now at Princeton, as well as myself and Haochen Wang. And what we did is we simulated a sample of FRBs. We ray traced them to get the DMs and then cross-correlated those DMs with galaxies. And we just compared the angular cross-correlation measurement with and without selection effects. And these FRBs were at a redshift of 0.4, and there were about 3,000 of them. So the first thing that we did was tested the effect of optical selection biases. So on the bottom panel here is the actual cross-correlation measurement. Without the bias is in white, and with the bias is orange. What we did is we just removed all FRBs originating from galaxies that were fainter than a magnitude of 20.7, which is a pretty aggressive optical magnitude cut. And here in the middle panel is the ratio of the two cross-correlation measurements, which is like completely consistent with one. So in other words, there's no bias that's introduced by optical selection effects, which is expected. So we also played around with the spatial placement of our FRBs on the sky. So we compared the cross-correlation measurement for FRBs that are kind of uniformly distributed over the sky to FRBs that preferentially traced galaxies with high star formation rates. And this also doesn't bias the measurement. So the cross-correlation measurement is really insensitive to the underlying FRB population that is measured. But what does matter are DM-dependent selection effects. So here, what we've done is place a pretty aggressive DM cutoff at 600. So don't see any FRBs with DMs that exceed 600. And if you look at the middle panel, the amplitude is suppressed by over 50% at small scales. So at least according to IllustrisTNG, the majority of the signal that we see in our cross-correlation measurement, it comes from a small number of FRBs with really, really high DMs. So it's important that our selection function doesn't remove those main contributors to the signal. And the good news is that if we place the actual CHIME DM-dependent selection function, we don't see much amplitude suppression. The caveat here is that this is specifically for a sample of FRBs that are at a redshift of 0.4. So you can imagine that if you were doing this with FRBs at a much higher redshift, the overall DM distribution would shift upwards, and you would be removing some of those really high excess DMs with your selection function. But at least for a local sample of FRBs, it seems like we're okay. Okay, so finally, what about CHIME Outriggers? We just came online, and we have yet to fully characterize our selection functions, even just our DM-dependent selection function, because the system is still kind of in a state of flux. But to kind of give you a sense of what we expect, this is our recovery fraction. So how many FRB triggers are we able to successfully localize with the full Outriggers array as a function of DM? And it seems like so far we're doing pretty good, at least up until a DM of 1,000. So what happens beyond 1,000 is our baseband buffer gets cut off, and we only have access to a fraction of our band. In general, the VOBI astrometry gets worse the less bandwidth you have. But the other thing is our RFI bands don't necessarily overlap at each site. So even if we have 100 megahertz of bandwidth that's accessible at CHIME, we might not have that much bandwidth accessible at the Outrigger sites if there's RFI contamination there. And the good news is that we're getting a baseband buffer upgrade, which will kind of remove a significant portion of this DM-dependent selection function, at least up until a DM of about 2,000 or so. There's other efforts that we're making to improve our sensitivity and kind of mitigate our selection effects, and Matthias will talk about that tomorrow. All right, I think I'm running low on time, so I'll just leave my conclusions here and take any questions now.
We'll start here. I'm going in anti-seniority order. Thank
you. I was wondering, you showed this important bias for the DM cuts at high DM, But of course, it's hard for a telescope not to have a similar cutoff at high DM. So I was wondering if you properly characterize your selection effect on the DM, can you avoid the bias that results from that?
You could forward model it. Yeah, but which would be harder because you would have to do that for every simulation you're testing with. Yeah.
Okay, so it will be dependent on a simulation. That's what you're saying.
Thanks, Shion. I think this is super cool. I was wondering whether you have some thoughts or you guys have thought about cross correlations with other tracers that are not galaxies. For example, intensity fields, intensity mapping, or UV background, things like that.
I haven't, but there are people who have. Calvin's thinking about doing this with lensing surveys, so I recommend talking to him.
Thanks.
Great. We'll do one more question. This must be a planet.
Oh, it's just you mentioned intensity mapping specifically. Intensity mapping is often hard for observables or line of sight integrals. Typically, they don't correlate because intensity mapping loses what are called the low K parallel modes, which are the ones that that contribute to those line of sight integrals. So those are generically.
Okay, let's Shion again.
Oh, hey, I'm here.
Great. And our next speaker is Zi-Liang, and they're going to talk about cosmological parameters from persistent radio sources. And you've got 3 minutes and 2 minutes for questions. So I'll give you a 1 minute warning.
Okay, can you see my screen and hear me well?
Yep, all three.
Okay. So good morning, everyone. My name is Zhang, a PhD candidate for UNLV. I'm very happy to have this chance to share our recent work about using FRB PIS system to do cosmology. Here's the outline of my talk. First, a short summary of PIS, and then I will introduce a very elegant model about the PIS, this so-called the luminosity IM relation, but I would like to call it the Young relation. Now, since we can obtain the intrinsic luminosity from a direct observable that is Rm, we actually have a standard candle. And in the third part, I will show you how we use such a relation to do cosmology. I'm not going to repeat the words about what FRBs and how they were discovered, since already have many sorrowful and wonderful talks from Monday to today morning, from history to current status. Now we have 4 confirmed PRS source until Tuesday and 2 PRS candidates from CHIME, Outriggers, and BLA. Yet I'm very happy to hear from Baryonic's talk Tuesday about using the EVN to confirm the 5th PRS system. So except we know the PIS are compact and steady, we also know their spectrum are non-thermal. They are more likely some kind of synchrotron radiation. So in 2020, Yuan Peiyang, Qiao Chuli, and Bin Zhang proposed a generic relation for synchrotron nebula. They refined their paper in 20 and 22. Here is the basic picture of their pitch model. There is a synchrotron nebula and a central engine of FRB. When the poles of FRB pass the nebula, it will take the DN and RM information in the nebula. Now, the key idea is in the nebula, you have 2 different electron population. One is the thermal electron, another one is the non-thermal electrons. And the break Lorentz factor is called the gamma thermal here. And then the thermal electron will contribute the Rn, and the non-thermal electrons will dominate the radiation of the PRS. There's a factor of fraction zeta E here, which is the ratio between the non-thermal electron and the thermal electron. We add the emission from all the non-thermal electrons, we finally get the luminosity of PRS. We then can eliminate the number density here and the magnetic field, and to get the relation between the luminosity and the Rm. Okay, as you can see, this elegant Yang relation can expand the observation very well, at least like few weeks ago. There is a new non-detection PIS of a very high DM, a very high ion FRB from the ATEL. So, but further follow-up observation are needed. Anyway, let's assume this Yang relation still work at least at this moment. Now, if we invert this relation and remind that IM of FRB is a direct observable, that means we can predict the intrinsic luminosity from an object in the universe. That means we can use FRB PIS system as standard candle. And if we expand the luminosity by the flux we observe, and if we know the Rm flux and the redshift, and plus this combination of this constant zeta, gamma, and R square, we can know the Hubble constant. But now there's actual things. We actually don't know this coefficient 1 over this 1 over zeta or something. In order to break the degeneracy between this coefficient and Hubble constant, we need an extra observable. We choose to use the Dn. By some simple algebra manipulation, we finally get a very ugly relation about this coefficient here. And if you are interested in the detail, please refer to our work. The archive number is here. Now we have a framework about using PIS to do cosmology, but the sample size is very limited. Except using the observation data, we decided to do some Monte Carlo simulation to generate some MOOC FRB PR sample to test our idea. Among this MOOC sample, the gray point here, only the blue point above the detection threshold can be observed, and we can assume the distribution of that coefficient. Now we have the MOOC sample. Our strategy is the two-step MCNC fitting. In the first fitting, we can constrain the coefficient zeta and gamma square and R square, and we can use the posterior distribution of this coefficient as the prior distribution for the next MCNC fitting, and we can finally constrain the Hubble constant. We can see here we successfully recovered the inject Hubble constant from the Monte Carlo MOOC sample. But for the real PR sample, we are not able to give a very good constraint about the Hubble constants since we only have 6 samples. Okay, here's the summary of my talk. I'm ready to take any question online or on Slack. Yeah.
Okay, unfortunately, we don't have time for questions on this one, so please put your questions in Slack, and Zi-Liang, you can monitor Slack there. The last talk of the session is the measurement that was talked about earlier. So Maryam, I'll let you take it away here. And you've got 3 minutes. I'll give you a 1 minute warning. I want you to have questions, so don't go over.
Hi, everyone. My name is Maryam Hussaini. I'm a graduate student working with Liam Connor, and I have about 200 seconds to talk to you about my science, so I better get to it. I am interested in the relationship between DM and large-scale structure, and more specifically, I try to do a stacking analysis in which I stack the DM as a function of the impact parameter of foreground structure, or like the galaxies in front of the FRB. But that doesn't, I don't know if that means anything to y'all. So let's go over what I did exactly. My apologies for the subpar art. I'm not much of an artist or a PowerPoint maker. But so we have the FRB coming in from the far right. That would be here. And we have us on Earth over here. It's not drawn to scale. And then we have all the galaxies that are in front of the FRB. Every time the FRB crosses close to a galaxy, it picks up a little bit of DM, a little bit, it passes through a little bit more material. So we measure the distance between the line of sight and every FRB, every galaxy that is in front of the FRB. And one highlight is not going to tell us much. So we do this for every single FRB that is in our sample. And then we make this plot where, like, in the x-axis, we have bins of impact parameter. That's the distance between the galaxies and the line of sight of the FRB. And on the y-axis, we are going to plot the excess DM for every bin that any FRB contributed to that bin. What we would expect is that, so for a plot like that, we would expect that at smaller distances, we're going to have a bit of a little bit more DM because, excess DM, because we expect if a signal is passing through the virial radius of a galaxy, it'll be going through more gas, so you're going to have more DM, and we would expect it to fade quite quickly after the virial radius of the galaxies end, so at larger scales. We see something surprising. I'm gonna pretend that the surprise hasn't been spoiled in previous talks. We don't see the signal fading quite as quickly as we had expected. The signal actually persists a little bit longer, up to megaparsec scales, which is far beyond the virial radius of most galaxies. So that is an indication that most of the excess DM, or at least some of the excess DM that we're seeing, must be coming from the IGM. We tried to test this with a simulation. So we run a similar analysis on TNG 300, and it's illustrated, unintended, on this plot that the halos, the contribution from the halo, that would be the yellow line on this plot, decays about as fast as you'd expect it to, but the IGM contribution to excess DM kind of persists longer than we had been expecting it. And then one last thing, I want to show you a special subset of the FRBs that we have. These seem to not be crossing any halos on their way to us. And we try and analyze it and get a value for FIGM, or the fraction of the baryons that would be in the IGM. And we get that at least 69% of the baryons are residing in the IGM. If you want to read more about my methods and the results, you can scan the QR code and read the paper. But thank you so much for listening to my talk.
Great. Questions for Maryam? Brian?
Hi, Brian Gainsler, UC Santa Cruz. Have you looked into whether your DM fall-off matches the RM fall-off that people are starting to see with background sources?
That's very interesting. We haven't analyzed that yet, but that would be cool to look at.
I can talk to you in the break.
Yeah, that sounds good.
And for one more question. All right. Cosmology.
Matt McQuinn, University of Washington. A really interesting result. I guess I didn't catch which sample you were using, and I also was interested. It looked qualitatively like the IGM with and this larger impact parameter extent, which really interesting that you find like will match. But I wasn't sure if quantitatively it was able to explain your signal.
Quantitatively, as in.
Yeah, or if you plot the curves on top of your measurement.
The simulation curve on top of the sample?
Yeah.
Oh, yeah. We can. I don't think we quite did that. But yeah, also I'm a big fan of your work.
And actually, very, very appreciated. What are the? Is this? Is this CHIME FRBs or?
It's. I'm so sorry. It's almost like everything but CHIME FRBs. But it's 61 FRBs that are localized, mostly DSA, some ASCAP. And again, there's a table in the paper that lists.
Awesome. Oh, I'll check out your paper. Yeah, that's super interesting. Thank you.
Yeah, thank you.
Okay, that closes out the session. So let's thank Maryam and all the speakers again. And coffee's served in the back there. You're so strange. You're so
Hello.
Okay.
Oh, shit.
Do you need this?
Do I need this? Welcome, everybody, to the continued session on CGM Cosmology. Next up is the lovely speaker, Stella Hawker, who's going to be talking to us about probing the CGM microphysics with FRBs and quasars. Give it up.
Give me a talk yet. I feel premature. Is this okay? Okay. Hopefully you can hear me. Okay. Okay. So today I will be talking about how we can leverage FRBs in tandem with other probes of the CGM, namely quasars, to learn more about the fundamental processes that are regulating multi-phase structure in galaxy halos. So as we've seen numerous times so far, foreground halos are very common along lines of sight to FRBs at greater than cosmological distances. But the contribution of these halos to the observed DM and scattering is debated. On the one hand, we see from the precisely localized FRBs that their pulse broadening and scintillation tends to be dominated by the interstellar media of their host galaxies and the Milky Way. And based on scattering budgets that are currently available for FRBs, we think that scattering in the CGM is largely negligible, although there are studies that suggest CGM scattering could become more significant at higher redshifts. However, there are also studies that suggest you could have significant scattering from the CGM, either generically due to the ubiquitous presence of cool gas or under special conditions. For example, Jacob recently led a nice paper showing that a highly scattered FRB detected by DSA 110 may actually intersect a high velocity cloud due to the rare overdensity of halos along its line of sight. So altogether, it's really unclear whether the scattering we currently observe from FRBs could have any plausible origin in the CGM, and more broadly, how to interpret the distribution of FRB scattering in the context of CGM physics. So today, I'm going to tell you how we can empirically predict the amount of scattering that occurs in the CGM using quasar observations, and thereby demonstrate how we can contextualize the scattering we observe in the landscape of other CGM probes. How do we do this? Well, it turns out that turbulence is actually observed in the CGM now, and where there is turbulence, there can also be scattering. So the first main way that turbulence is actually observed in the CGM, and arguably the most direct way, is through integral field spectroscopy, or IFS, of CGM emission around bright quasars. So how this works is that you have a spatial map of radial velocity fluctuations in the CGM, and you use this to construct the velocity structure function, which you can see an example of on your right. So you can see that in this particular case for the CGM around a quasar at a redshift 1, that the velocity structure function that's observed, shown by the black points, is actually beautifully consistent with Kolmogorov turbulence, indicated by the orange dashed curve, between spatial scales of roughly 5 to 50 kiloparsecs. These observations are thought to predominantly trace turbulence in the hot gas of the CGM. The next main way that turbulence is now inferred in the CGM is through measurements of non-thermal broadening of quasar absorption lines. So these absorption lines yield non-thermal line widths, which are shown on your right, and separate photoionization modeling of the absorption line profiles yields the densities, temperatures, and sizes of the cool clouds that are responsible for these absorption lines. And so when you compare the distribution of non-thermal line width to cloud size, which are two independently inferred quantities, you see that they are broadly consistent with a power law as expected from turbulence, and broadly consistent with, albeit a large amount of scatter, with the power law expected, again, from Kolmogorov turbulence, but this time over smaller spatial scales from much less than a kiloparsec up to a kiloparsec. And again, these are based on absorption lines that are tracing predominantly metal ions that are produced by cool, roughly 10 to the 4 Kelvin gas in the CGM.
So we can use these quasar results to anchor the turbulent power spectrum at large spatial scales. So here you can see a notional sketch of the fluctuation power spectrum as a function of spatial scale. And so quasars provide us with constraints on velocity fluctuations at the largest spatial scales in this spectrum. Now, because density fluctuations arise as a passive scalar in a turbulent cascade, they are related to the velocity fluctuation spectrum by the Mach number. And so it turns out that the two power spectra of the velocity and density fluctuations, which are shown on the right, can be directly related to each other, again, via the Mach number. So if we assume that the turbulence responsible for these velocity fluctuations observed actually extends all the way down to the scales where turbulence is expected to dissipate, then we would expect a range of observable effects from FRBs. So between roughly the Fresnel scale on the order of a few AU to the sizes of typical clouds, you might expect various refractive effects, which I'll actually largely ignore, but I refer you to Luis's talk later for more discussion of that. Below the Fresnel scale, we would expect various diffractive scattering effects. These include angular broadening, pulse broadening, and diffractive scintillation. And if dissipation of the turbulence occurs at plasma kinetic scales, which would be on the order of hundreds to thousands of kilometers in the CGM, depending on the gas phase, then we would expect that FRBs will be scattered by these density fluctuations, and that in fact the FRB scattering that's observed will be sensitive to density fluctuations going all the way down to those kinetic scales. Now, how does this work? Well, if you remember Robert's talk, he showed us that density fluctuations at the smallest length scales in a medium are responsible for the largest scattering angles and hence the longest time delays. And so if you have significant density fluctuations at spatial scales much smaller than the so-called diffractive scale, then you would expect significant scattered flux in your FRB at time delays greater than the diffractive scattering time that's commonly measured. What do I mean by this? Well, there are two ways of looking at this. Here you can see a cartoon on the left of a scattered image. Typically, we assume that the scattered image is a Gaussian. And so the angular broadening or characteristic scattering angle that you infer is related to the diffractive scale or our diff. But it turns out that if you have density fluctuations going all the way down to kinetic scales, then you would not expect a Gaussian scattered image. Instead, you would expect an extended halo with these long wings in the image. And those wings precisely arise from the density fluctuations at these tiniest spatial scales. If we translate this to the shape of the scattered pulse, then instead of seeing an exponential scattered pulse, we would instead see a pulse with a very extended scattered tail, and the extent of that tail would depend on the inner scale. And so it turns out that in this regime, which we actually expect to be the case in the CGM, where you have density fluctuations below spatial scales equivalent to the diffractive scale, then it turns out that your scattered pulse will have a mean delay that is greater than the 1/e time that's commonly measured. And critically, this mean delay will depend on the dissipation scale, or often referred to it as the inner scale of the turbulence spectrum. So for this reason, we can now actually use the quasar observations to predict the level of scattering in the CGM, again, assuming that the turbulence extends across this huge range of spatial scales, all the way from the fraction of a kiloparsec up to 50 kiloparsecs probed by quasars, all the way down to the thousands of kilometers probed by FRBs. So here you can see a general schematic of the methodology. So we have two different tracers of hot and cool gas turbulence, which I just described. We use the velocity fluctuations to infer the amplitude of the density fluctuation power spectrum, Cn squared. And then we use this to evaluate this composite density fluctuation parameter F tilde, which I'll describe in a moment. And this then gives us a prediction of the scattering timescale. So I've shown a version of this slide, I think, at every single FRB meeting I've ever attended. So I apologize to those of you who keep seeing it. But this time it's a little bit different. So we can relate the mean scattering delay to the underlying density fluctuations via the simple proportionality here. It's related to the observing frequency nu, this geometric leverage factor, G-scat, which depends on where the scattering medium is located along the line of sight, the DM of the scattering medium, the redshift of the scattering medium, and then finally this composite density fluctuation parameter, F tilde. So F tilde is related to both the statistics of density fluctuations in the medium. So this includes the properties of cloudlets, the volume filling factor of those cloudlets, variations in the mean density of the cloudlets. And it depends on the properties of the turbulence cascade. So you can see here in this proportionality that F tilde is directly related to Cn squared, the amplitude of the density fluctuation spectrum, as well as the dissipation scale Li. Okay, so what do we actually predict? So using the quasar results that I described, we can predict both Cn squared and the fluctuation parameter for both hot and cool gas in the CGM. And you can see here on the left that the Cn squared values we infer, this is again the amplitude of the density fluctuation spectrum, it's orders of magnitude smaller than values we typically infer in the ISM from pulsars. When you look at the hot gas and the cool gas, you can actually get up to values that are comparable to what we encounter in the ISM. Similarly, on the right, you can see that the fluctuation parameter behaves in a similar way. One important caveat is that in the cool gas, these values of Cn squared and F tilde are inferred based on properties of turbulence within individual cool clouds. And so these are really local quantities. What do we get for scattering? So here on the left, you can see the distribution of the mean scattering timescale and the scintillation bandwidth in the scattering lens frame for the hot CGM. And then on the right, you have it for the cool CGM. And one of the main things we find is that, unsurprisingly, observations of turbulence in the hot CGM indicate that you would get negligible scattering regardless of if your halo happens to be placed fortuitously along the line of sight with large geometric leverage. By contrast, in the cool CGM, you can actually have detectable scattering, but only in cases where your DM and geometric leverage are large. But if you examine the actual values of the scattering timescales and scintillation bandwidths shown here more closely, you'll see that in practice, these values may actually be indistinguishable from the galactic ISM. Now, another fortuitous thing is that because these quasar observations give you an independent estimate of this composite density fluctuation parameter from the FRBs, you can actually combine the two to place a constraint on the dissipation scale of the turbulence. And so here you can see a comparison between the fluctuation parameters we infer from quasar results relevant to the cool and hot gas compared to two different FRBs that intersect foreground halos. And long story short, we see that the upper limits on F tilde for these two FRBs give us a constraint on the dissipation scale that's comparable to plasma kinetic scales. In future, if you have a really firm constraint on scattering in the CGM, then this could become a much more powerful constraint. Now, it turns out that you don't even need to detect scattering from the CGM in order for that to be informative. So all multipath propagation, whether it's diffractive or refractive, requires that you have density fluctuations at spatial scales much smaller than the so-called multipath scale. Here you can see the multipath scales that we predict as a function of the integrated Cn squared that we infer from quasar results. And one of the things you see is that in cool gas, the multipath scale is on the order of 0.01 to 1 parsecs, which indicates that you would need to have density fluctuations within cool clouds in order to produce scattering. And so if you can say very conclusively that there is no scattering happening along a CGM on your line of sight, then that implies that dissipation, at least for the cool gas, would be at roughly cloud scales. Okay, so here's my brief summary. The main point I want to leave you with is that this is all demonstrative, right? But ideally, we would actually combine quasar and FRB sight lines through an individual galaxy halo. And with sufficient observations, you could then use those two observables in tandem to constrain the amplitude, the spectral index, and the dissipation scale of the turbulence. All of these methods are also applicable in the ISM of FRB host galaxies, which could be readily studied in a mission. And if you were confused by anything I said, please come talk to me later or read the paper, which is linked here. Thank you.
Heidi, we have time for a couple questions. Couple questions for Stella? Oh, my bad.
Ilya Kriken here. How many quasar sidelines do you need to actually put constraints on all these parameters? If I missed this, like in real observations, how many do you need to put side constraints?
Yeah, well, in principle, if you have an FRB and one quasar sightline that happen to be superimposed or very, very close to each other, then that might be enough. But on the other hand, maybe having a large sample of FRBs and a large sample of quasars through one halo, like we have in M31, would be the better way to go. It really depends. So I think, yeah, depending on the sample you have, you could get varying levels of precision in your constraint, basically.
Thanks.
Online.
Sunil, can you unmute yourself and ask your question, please?
Right, thank you. Sunil here from Northwestern U Chicago. Great talk, Stella. I was just wondering when you mentioned that similar measurements could be made for the ISM. I wonder if you have looked into the velocity structure function for like manga galaxies or something like that and tried to put constraints on the scattering in the ISM.
Yeah, it's a great idea, Sunil, and the short answer is no, I haven't done that yet, but I think it would be really cool to do.
Cool, thanks.
Liam, you can unmute yourself and ask your question?
Hey Stella, it's Liam from the previous session. Great talk. This seems like a powerful idea. I know you thought a little bit about simulations. Can you speculate on how this could be done in like a zoom in fire simulation where you forward model both the quasars and the FRB scattering?
Yeah, so the short answer is I think we could definitely do this in FIRE. We would probably need to use a subgrid model, and basically all of the analytic expressions that I provide in my work, I think would be the basis for such a subgrid model. Yeah, so I think it's doable.
Awesome. All right, let's get to another round of applause. And next up, I'm going to online.
Yeah.
We have Laura Trevina, who's going to tell us about probing the M31 halo using dispersion method of FRBs. Laura is online. Amazing.
Hello, everyone. Can you hear me?
Yep, we can hear you. Go ahead and take it away whenever you're ready.
All right, thank you so much. So my name is Lodrick Kahinga. I'm a PhD student at UCSC. And once again, thank you for inviting me for this talk, where I'm gonna talk about essentially just studying the M31 halo or CGM using FRB dispersion. And below are some of the main contributors. I work with X and Sunil and Calvin, and both were very essential for this work. And I cannot understate the contribution from the above collaborations, namely F4 and CHIME. And the sample actually I was using for this analysis was the CHIME FRBs Medlock 2. And so, I don't think I should even go into this. We've seen a lot of talks from Monday with Sanskrit Das and Matt McQueen and Liam Connor, and Ralf did a very good summary for what this is today. So I won't even go into it, but just as a reminder, it's basically when you're thinking CGM, it's the connecting medium between the ISM and the IGM. And this plot on the right here is just to sort of show all the stuff that's happening in terms of feedback and gas exchange and all these things, all these fun things happening in the CGM, and we would want to understand that. But I will be focusing on basically one question, and the second question is sort of related, where I'm just thinking of what is the baryonic mass inside the CGM? And this, I think, just rolls off part of the strong missing baryons problem that Liam Connor was talking about earlier. And another thing that we sort of want to think about in terms of distribution of baryons is just how many of these baryons are inside the halo? How many does it retain after they fall into the halo? And so this is basically the two questions we set out to sort of think about. And we were especially looking at the M31 halo.
And so the M31 halo, as you know, is the Andromeda Galaxy. It's the nearest galaxy here. It's an L-star galaxy. It's very similar to the Milky Way. It subtends, it's about 770 kiloparsecs away. It subtends about 30 degrees in the sky, which is fantastic because when you're thinking about for example, the CHIME sample or the unlocalized FRBs in CHIME, they have 0.2 degrees, about 0.2 degrees square on average localization. And so when you look at the plot on the left here, this is 0.2, and sort of this is about 30 degrees, and this is all 300 kiloparsecs. And so you can confidently assign what FRBs are going through the halo and what FRBs are not going through the halo, and that's great. And you can get quite a few FRBs going through M31, and we'll talk about that sample later. Another property that you might want to think about is the mass of the halo. And that's about 10 to the 12 solar masses. And so that's great. It's a very Milky Way-like galaxy, maybe a little bit more massive. But yeah, so then how would you essentially do this? So you'd have a sightline. It's going through the M31 halo. You'd have another sightline that's not going through the M31 halo. In our case, we're using FRBs that are not localized, and therefore they have no redshifts. But as Sunil was talking about yesterday, not having redshifts in your FRBs doesn't stop you from doing science, and so that's essentially what we're trying to do here. So we're trying to compare the M31 FRBs, that is FRBs going through the M31 halo, and the ones that are not. And so statistically, the ones going through through M31 should have some excess DM, if you like. And so here's a CHIME sample. Nam and Jane did a wonderful job of describing catalog 2 yesterday, or the day before that. And so what I'm just going to mention here is that on this plot, the blue sightlines are the FRBs we're going to be using, and the yellow sightlines are excluded. The reasons we're excluding these yellow sightlines that are within the ±5 galactic latitude, it's close to the galactic plane, and have a DMISM greater than 100 parsecs per cube is we want to exclude all the FRBs that are sort of have a high Milky Way contribution. And so once you do that, and basically the black line here is just showing where the Andromeda Galaxy would be in galactic coordinates. And so once you do that, then you sort of think about more sort of selection. You want to make a better sample. And so what we do here is something we call a differential experiment, where essentially you want to use the M31 FRBs, or the FRBs going through the M31 halo, to essentially construct a control sample. How you would do this is you would match FRBs, the FRBs, the M31 FRBs and the non-M31 FRBs, or sightlines that are not going through the halo, and you'd use the M31 FRBs to essentially, you're matching FRBs that have similar galactic latitude and that have similar DMISM, or the disparate major contribution from the ISM. The main reason we're doing this is just to have very similar distributions in terms of Milky Way contributions, such that when you essentially measure any M31 contribution, it should be attributed to just the M31 halo itself, and not some discrepancy between the Milky Way contributions between the two samples. So that's the whole motivation behind making a control sample. And so just speaking of the M31 signal, or rather the M31 contribution, this plot is just overplotted against an MNFW prediction of what would be the DM when you're looking at the halo. And so just to give you an idea of the kind of signal that we are thinking about, and we have maybe 100 parsecs per centimeter cube, sorry, getting ahead of myself. Would have about 100 parsecs sort of centimeter cube sort of contribution there. And so how would you compare these two samples now? You have your M31 FRBs, you have a control sample. The first thing you think about is just going for a case analysis. And so we did that, get a p-value of 0.24. So it's not a statistically significant detection. And so what you'd expect when you look at the plot on the left, you split the M31 FRBs to have like an apparent shift on the CDF towards the right, which is not apparent for the higher DM, but it's kind of apparent for the lower DM, which is where we're expecting most of the DM contribution to be. And so this then prompts you kind of have to think about a weighting scheme. So how much signal does each particular sightline have? And so to think about this, so once again, think about dispersion measure as sort of a proxy for distance, if you like. And so if you have, for example, the red line here is showing just some sightline which have a high DM and so longer. And so if you have an FRB with high DM, a lot of the signal is going to be IGM and maybe DM host and all these things, and a small fraction of it is going to be the M31 contribution. And so it essentially a high DM FRB will have a lower signal to noise ratio in terms of M31 dispersion measure contribution. In contrast, if you have a lower DM FRB, like the blue line here, most of the signal is going to be from the M31 halo. And so that then means that you're going to need a weighting scheme, or we apply a weighting scheme that upweights the lower DM and then lower and then gives lower weight to the higher DM FRBs. And so we adapt a weighting scheme that's very similar to the Wu and McQueen. Actually, it's identical to Wu and McQueen paper back in 2023, as shown in the above sort of exponential weighting scheme. And so we went and did this. So essentially what you do is just take a weighted mean of FRBs going through M31 and the control sample, and that should give you some excess DM, if you like, or the M31 contribution, which is these error bars shown here. We wanted to make a DM profile. However, we couldn't. We only could bin it into two regions essentially, and that's because of the data. We could only allow two bins, but as you can imagine, with more FRBs, you want to have more bins. But what else can we do? We can also try and constrain using different models. And so the shaded region here is sort of that constraint, which we do. So what we do is we define a goodness of fitness statistics shown in this equation here. And what I want you to think about looking at this equation is just, this is an observed DM, and this is DM predicted from some model. And so once you do, we sort of do, you subtract one from the other. And then if you have your perfect model, this number should be as low as possible. You normalize that to get a chi-square. And so your best model would have the minimum chi-square, essentially. And so you can use that to, if you have models, yes.
Lordrick, you have about 1 minute left.
Okay. If you have different models, you can then constrain your mass. And so actually I'm almost done. And so in conclusion, we have used those DM to constrain the mass. What I want you to sort of also think about, at least if you take the mass constraint as face value, it appears that M31 has retained most of its baryons, but once again, we still have very, very large error bars. So we predict that maybe if you have 20,000 FRBs, you can first of all, you can have 5 radio beams with greater than 95% confidence limit, and you can also do a really good job of constraining the mass. So just lastly, we're going to look out for this paper, probably somewhere towards the end of this month. It's going to be on archive, and I would love questions and to chat. Thank you.
Thanks for a great talk, Lordrick. Does anyone have any questions? Yes.
Thanks, Lordrick. This is Duncan Lorimer from WVU. I was wondering if there are any significant differences in the sensitivity of CHIME in the control sample versus the M31 sample. And did you take those into account?
Come again, I'm wondering sensitivity in terms
so the two samples are in different parts of the sky, and so presumably there's some difference in the sensitivity of the instrument in those different areas, and that could lead to different DM ranges.
Okay, that's a good question. I guess I hadn't considered that the main motivation, like I said, for the control sample is just to get very similar distributions in terms of Milky Way contributions. But I guess I'd have to think about that. Thank you.
Okay.
Yeah.
Awesome. All right, let's maybe move the rest of the discussion to Slack. Give Lloyd another round of applause. And next up, we'll have Luis Mas-Ribas, who's going to tell us about scattering in the CGM, refractive scattering in the CGM.
I'll get 2 minutes. 2 minutes. Okay, thank you all for being here. Can you hear me all right? Yeah, okay, excellent. So yes, I'm Luis from University of California in Santa Cruz. And we have a paper on archive that I want to talk a little bit about that we did together with Matt McQueen and my boss, Konietzka. So let's get to it. So we have heard a lot of CGM during these days, especially today, and tomorrow we will hear a bit more, but I just wanted to re-emphasize. Lordrick just mentioned this, Stella did as well, but let me just say a bit more or again about the CGM. So why do we care about the CGM is because where cool stuff happens. So the CGM is the separation between the IGM and the galaxy itself, and it's where cool gas is accreted that will be reused to form stars, and at the same time, these stars produce metals and materials that is re-ejected and enriches the IGN. So if you are interested on galaxy formation and galaxy evolution, you want to understand the circumgalactic medium. And for doing that, we would like to know all the physical processes that are happening in the CGM. And today I'm gonna focus on, in particular, on two properties or two parameters, which are the density and the size of the gas clouds in the CGM. And this is because the physical processes that happen in the CGM shape these two, or the values of these two parameters. And on the other hand, or vice versa, if you know the sizes and the densities of your gas in several regions, for example, then you get information about these physical processes. So that's what we are trying to do. Also, we will be looking at extragalactic halos. So as Ilya Trikin and many others have emphasized, and we are starting to see, we should not only care about the host and the Milky Way of the host of the FRB and the Milky Way, but it's also possible that intervening halos contribute to the quantities that we measure, DM, magnetic fields, scattering. So we would like to quantify how much this contribution is. And in particular, if you imagine that these intervening halos contribute a lot to scattering the FRB signal, this signal can be so diffused that maybe we are not seeing some FRBs just because the signal gets very, very scattered. So that could be one possibility. Also, as we heard, especially on Monday from Robert Main, who is a great astronomer and karaoke singer, as we discovered last night, these halos could also impact the scintillation that we observe in the Milky Way. This has been discussed in many papers. For our work, we have been following very closely Dylan's Joe fantastic paper, which also treats this aspect. And this has the name that I would call the two-screen system or the two-screen scenario, depending on the distance between two halos or screens, if they resolve each other, depending on the properties of one and the other, the scintillation of the Milky Way can be suppressed by the other and so on. This usually happens considering the host on one as one screen and the other being the Milky Way. But what I'm trying to say here is that these intervening halos can act as the host and they can also impact the scintillation from the Milky Way. Okay, and why refractive scattering? I think Stella just gave a super beautiful talk that took care of most of diffraction here, but I just want to remind that the two parts of scattering that we have in radio scattering in radio are refractive and diffractive regimes. And they are usually separated by the Fresnel scale, and this means the size of the scatter of this radiation. When you have scatters or gas clouds or particles that are very small below the Fresnel scale, then you have diffractive effects. If you have clouds that are large, then you observe refractive effects. That corresponds, if you look at refraction, that corresponds to scales of parsecs and kiloparsecs. That's the refractive regime. And that to us is interesting because we can make clear and simple comparisons with observations. It's difficult to have observations of very small scales when you think about observations from gas effects and such. So another cool thing about refraction is that it's very simple, the formalism. So I just wanted to show you 2 or 3 equations here because I think we can all understand how this works. And to me, it's a very clear picture of the science here. So imagine that your medium is empty and you have some clouds of given size and density, and then you have light going through. This ray is hitting 3 clouds here, and then the wave phase of this ray will be advanced. And the advance of this wave will depend on the size of the clouds, how many clouds you hit, and their density. So all the time you can see that I'm playing with the density and the size of these clouds. But you don't only have one ray, you have a wavefront that hits different paths. And because sometimes you hit more or less clouds, what happens is that in the end, you will bend your ray. So this change of direction corresponds to that angle, and that's what we call refractive scattering. So now you can understand that if the light, instead of going straight, is going to take some angle, it's going to take a longer path. So the light that goes in that path is going to arrive later than the one that goes straight. So that results in a time delay, which is one of the quantities when we talk about the scattering. And here you have, again, the dependence with densities and sizes. And another important thing, very important, that I learned also from Dylan's paper is that you have to consider that we need multiple images for this to happen. So by definition, the time delay is the time delay between images that take different directions. So if you only have one image, there is no different directions. So there is no effect. And you can see that there's a strong dependence here on the size of the clouds, meaning that when you have, was this very small or very large? I forgot. Very small or very large clouds, very small, then the number of images that you produce is very small. So this will be a limiting factor for whether or not you will produce scattering, a strong constraint. Okay, let's apply this. So let's imagine now that we have a halo that is 10% fill of these clouds. They are all the same size. They are all the same density for simplicity. And you have the 2 equations here. So let's fill this parameter space. And this is what we see here. First of all, I just want to highlight this range between these vertical lines here. These are the inferred densities that come from quasar spectroscopy, quasar absorption lines. So most of the gas in the CGM tends to be, or is expected to be, between 10 to the minus 2 and a few times 10 to the minus 3 particles per cubic centimeter. So this is what we expect most of the CGM gas. And you can see in the parameter space that big white area on the upper part, and all that white area corresponds to where scattering by this halo cannot produce more than one image. So there is no scattering effect. In other words, all that parameter space does not affect a scintillation, does not impact the FRB signal at all. So in other words, most of the gas in the CGM of this halo does not affect the FRB signal. That's one main takeaway. There are other regions down here where we could have high density. We are going to the right side, so this is high density and quite around 1 parsec size. These dense clouds of gas, these ones could impact a scintillation. We expect this gas to be localized more in the center of the circumgalactic medium, and actually these sizes and these densities correspond to what Jacob found in his paper, that maybe something like a high velocity cloud could be responsible for scattering. This is the type of objects we are talking here. We know these exist in the Milky Way. We don't expect them at 100 kiloparsecs, perhaps, but they are close to the center. So these ones could affect the scintillation, meaning that they could suppress scintillation. So these are my two main takeaways here. But cool thing, if we care about the dense gas, which we do in the CGM field, we can try to put constraints to for this dense gas. In particular, even hitting one single cloud of gas with very high density, 1 particle per cubic centimeter, and 0.1 parsec, that is enough to suppress a scintillation from an FRB, say at redshift point something, and at 1 gigaparsec you have one of these clumps, and that would be enough to suppress a scintillation. So then you can wonder whether you can use that to put constraints on this gas. And in particular, this gas in the CGM is usually traced by a metal, or ion, which is the one-time ionized magnesium. So there is a large bibliography or large literature about magnesium-2 gas clouds to explain the CGM. So the idea here is to make connections between FRBs, this dense gas, and then to magnesium. And in particular, we are checking all this with mouse and salmons and some others. The idea here is that if we take a large number of FRBs, for example, CHIME catalog 2, and we look at what fraction of these FRBs have suppressed the scintillation, that would give us kind of a limit of what's the probability of hitting one of these clouds in all of these sidelines. So that in turn could give us constraints on this dense gas, the size, the densities. And if we talk about magnesium-2, then we talk about the equivalent width of the absorption lines. And just some preliminary calculations depending on how big these clouds are, the densities, and the equivalent width of the magnesium-2 absorber systems, the large lot of data in the literature. We can see that we expect suppressions that go from a few percent to tenths of percent. But this is just some theoretical calculation. We are waiting for the data. So in summary, refractive scattering, which if it happens is added on top of any possible diffractive scattering that Stella has been mentioning. We would account for both of them. Most of the gas in the CGM seem to not play much of a role for refraction, but the dense clouds that we expect to be closer to the center, if you intersect them, which is not easy, the probability is low, if you hit one of those could contribute and they could impact a scintillation. So when you do calculations of a scattering, please remember about refraction, especially if you expect some dense gas or something, think about it. And if more statistically, using a large population of FRBs, you can think that what fraction of those are non-scintillating, and then try to connect that to, yeah. I lost my line of thought now, but I'm pretty much done. And I don't have any picture of a pet or anything, but I just took some pictures last night that I just wanted to put here, and I'll leave it here. Thank you very much.
Thank you so much, Luis. Any questions? Yes.
$50.
I am curious regarding the N images. Can you go back to the formula? So, what? I'm Barak Zakai from Weizmann. So, this N images, yes. It seems to me that you can actually measure it if it's less than 1,000 using the high SNR bursts. Do you find this particular measurement useful? Do you think this is a good thing to do?
Sorry, I missed you said thousands? Or?
I think that if N images is smaller than 1,000, you could actually get an estimate of it from the actual scintillation pattern, from its fluctuations.
Okay.
Do you find this measurement useful?
I would like to know more about this because I have not thought so much about that. So what we think is the more images that might help somewhat or contribute to the extended tail somewhat, but I think the diffraction is multipath propagation is more responsible for the extended tail. From the scintillation, you could infer the number of images. That's what you're suggesting?
Yes.
Okay, I would like to know more because I don't know much, but yeah, I would like to hear more about this idea. Thank you.
All right, let's go to Luis again.
Online.
Online.
Yep. So, Ralf, if you could share screen.
Yes, I'll do that. Can you confirm if my audio is okay?
Yep, we can hear you.
Awesome. Can I start?
Yes. Next, I'll just introduce you real quick. We have Swalali Patil, who's going to tell us about a spatial gap in the sky distribution of FRB detections coinciding with galactic plasma over densities, potentially answering some of the questions that we were all just wondering about. But yes, take it away.
Thank you, Jacob. And thanks the organizers for organizing this virtual mode also so smoothly. I'm Swarali. I'm a PhD candidate at West Virginia University, and I'm going to present about my upcoming paper on the spatial gap that we see in FRB sky distribution in the catalog 2 of CHIME FRB. So FRBs, as we know, are excellent probes of the intervening media and because of their propagation effects. And scatter broadening can smear FRB signals below the detectability thresholds. Like you can see here, there is a crisp FRB coming from an extragalactic source, but as it travels through intervening medium, it gets smeared out. And this effect is especially pronounced at low radio frequencies. And so it's known that we see fewer FRB detections in the galactic plane. It's also postulated that scintillation boosts faint FRBs above the thresholds at higher galactic latitudes, but within the galactic plane, this effect is suppressed because of scattering. So Stella wrote this fantastic paper, Stella and her collaborators, where they defined this galactic scattering zone of avoidance, which is a frequency-dependent region of the sky where enhanced scattering suppresses FRB detectability. And they quantify this really nicely in this plot where they have plotted the signal-to-noise reduction factor as a function of the observing frequency. And as you can see, it is more pronounced in the chime band, which is at lower frequencies. And based on the estimates of DM and scattering timescales from electron density model NE 2001, they postulated the area, the galactic latitudes and longitudes that are spanned by this galactic scattering zone of avoidance. And previous studies of FRB sky distribution have been limited because of fewer FRB detections, and also difficulties in combining data from different instruments because of their differing sensitivities and selection effects. And these studies have been mostly focused on the galactic latitude trends. For example, these two independent studies by Emily Petrov and Sarah. Even in Catalog 1, with a sample of 536 FRBs, Alex Josephi and collaborators found no significant dependence on galactic latitude. However, with CHIME Catalog 2, we have a sample of over 4,500 FRBs. The catalog is coming out soon. And out of these, over 3,600 are unique lines of sight. So that gives us an opportunity to probe these effects along all these unique lines of sights. And this is the largest uniform sample from a single instrument to date. And so what do we see in the Catalog 2 spatial sky distribution? We see this visually striking gap in FRB detections depicted by black dashed lines here. And the white markers are all of the FRB positions in Catalog 2, and the cyan points are FRB sight lines that intersect through H2 regions. I'm going to come back to that later. And we find that this zone of avoidance or detection gap spans between these galactic latitudes and longitudes. And this aligns with the Cygnus X region, which is a dense turbulent star-forming complex within the Milky Way, and it's rich in H2 regions. Our total sample of FRBs was 3,165, and it's overlaid on the Fink-Banner H-alpha intensity map. And as you can see, there is you can qualitatively see there is an anti-correlation between the intensity of the H-alpha map and the number of FRBs detected. And here is a zoomed in view of the detection gap. It's roughly circular, centered at those coordinates. And we use triangulation to find the convex polygon that encloses this detection gap, and the area of that was 237 square degrees. And to check whether this is just a mere chance, we use rejection sampling, accepting positions based on the sensitivity and exposure for 1,000 realizations, generating twice the number of FRBs that we see in catalog 2. And we find that this detection gap is extremely highly significant with a very low p-value. And this is a strong evidence against the random chance. There are some other alternative explanations that we test are free absorptions, which is negligible at the CHIME frequency, misclassified sources from FRBs being missed due to the CHIME detection pipeline DM cutoff. But that can be ruled out very easily because in this, especially along this line of sight, the bias is in the other direction, meaning DM is heavily underestimated. Pulsars misclassified as FRBs could be a possibility. We do not see any repeat bursts in the current sample that we use for this study, but this can't be conclusively ruled out. We would need separate dedicated studies for that. DM smearing is also not that dominant, but we would need a selection function for updated selection function for catalog 2 to make conclusive statements about that, because we know that even though high DM values are underrepresented in the catalog in CHIME FRB, those are not rare. So we don't see that as being the main cause behind the detection void. And the diamond, red color diamond that you see here is the only FRB that's been detected in the detection void, and that's the fast FRB from the Galactic Plane Pulsar Snapshot Survey, and that has a DM of approx 2000 parsec per cubic centimeter. Another extremely scattered pulsar that we see in the detection gap is J2022, and that's known to be lying behind an H2 region. And so, based on what we know from catalog 2, even though we don't have an updated selection function, what can we say about the data that we have and the intrinsic properties of the bursts that we have at hand right now? And so, if we plot the scattering timescale and intrinsic burst widths of these bursts, we can draw detectability curves for a fixed value of flux based on the single pulse radiometer equation in this burst width and scattering timescale space. And so we use the fit burst parameters for both of these burst width and scattering timescale. And we use a well-measured scattering timescale cutoff at 0.13 milliseconds. And basically what we are doing here is assuming a hypothetical scenario where all the bursts were to lie behind the detection void. We check if we would still detect them given the foreground effects or not. And on the top panel, you see a cumulative distribution function of the detectable bursts for 2 different fluxes and the probability distributions for 2 different fluxes, namely blue is the 90th percentile and orange is the 50th percentile. And what we see from this is the lower limit on the scattering timescale along this line of sight, which is 4.36 milliseconds. And so this was about the Cygnus X line of sight, but in general, are we missing highly scattered lines of sight in our sample? And so what you see here is on the background, the Fink-Banner H-alpha map, and the black contours are the intensity contours logarithmically plotted. And a good laboratory for ionized medium within the galaxy are H2 regions. So we check whether these FRB sight lines pass through H2 regions, and the white circles that you see are the the H2 regions from Wise catalog. Cyan points are the FRBs that do not intersect through these H2 regions, and lime points are the ones that pass through them. Here is the detection gap, and the size of these markers is scaled based on log of their scattering time scales as measured by Fitburst.
Swati, you have about a little over a minute left.
Okay, I'll wrap it up. The case statistic of scattering timescales of intersecting and non-intersecting FRBs is not that significant, even though the mean values differ a lot. So we plot this emission measure comparison for all of the CHIME visible sky versus at the FRB locations. And what you see here is the weighted number density. And so we can just, to conclude from this, we can say that there is a FRB deficit at higher emission measures. So FRB sightlines tend to avoid higher emission measures. And I'll leave here my conclusions for you all, and I'll be happy to take any questions here or on Slack. Thank you.
Thank you so much. That was an amazing talk. Any questions? Yeah. Oh man, I don't want to throw it that far.
Thank you. Really beautiful talk, Swarali. This is Stella. I was just wondering, have you considered also trying to do comparisons to other tracers of dense ionized gas like radio recombination line maps? Because these H-alpha maps are inherently limited by dust extinction, particularly for, lines of sight that are integrating across the entire galaxy.
Yeah. We tried looking for some data and couldn't find it in the archives, but that's a really good suggestion, Stella. I think it will be something super important to try out. Yeah.
Any other questions? Yeah.
Hi, this is Adam Dong from NRAO. I was wondering, I guess a really cool goal was to probe the material in this cloud. So to do that, one of the easiest ways would be to detect an FRB in this region. Is there any chance of doing it through, for example, imaging? If you integrate over 10 milliseconds or something, and so you don't depend on DM or scattering, you're just integrating the intensity there.
Are you saying with CHIME or?
No, not CHIME. Like, let's say you got VLA visibilities in that region, and you just image it with like fast imaging, like real fast can do, or something like that.
Yeah, I haven't thought about that. We did check if we would see some sort of if we can resolve basically scattering with the CHIME outriggers, but I haven't thought about this. Thanks, Adam. I will write that down.
All right, let's move the rest of the discussion to Slack. Thank Swarali again.
Thank you.
All right, lovely. Finally, we have a lightning talk by our very own local verificator on searching and identifying coherent phase correlations from multipath propagation in FIMA from baseband data. Yeah, right. Dave, do you want a minute at the end, or? This already.
Okay. Okay. Hi, my name is Ralf. I'm a PhD student here at McGill, and my primary research interest is working on searching for coherent lensing and trying to develop methods to identify them and applying these search methods to CHIME baseband data. Yeah, so over the past year, we've been developing a simulation tool to model coherent lensing as it propagates through different lenses. This simulation tool works in the iconal limit which is to say it's the merging point between geometric optics and wave optics. So it takes considerations of rays, light rays, but it considers the phase information that gets propagated along with it. And we use the simulation tool to model coherent electric fields as they propagate through multiple lensing scenarios as they make their way to a radio telescope. And so, yeah, as just an examples, we model everything from gravitational lensing to plasma lensing and even multiple screens, such as a 2-screen scattering system that I'm showing here. It's all available as a Python package that should be pretty easy to install. And I do want to highlight that I am going to focus on FRBs, but really this works as modeling the electric field propagation in the iconal limit as long as you have a point source. And so the main focus of this tool has been to try and understand the phase decoherence that can happen, especially when you have a gravitational lens and some scattering along the site. And what we've really been trying to do is use the simulation tool to test and evaluate which lensing systems can maintain this coherence to an observer and what observables can they provide that we might be able to measure this degree of coherence. And so at CHIME, we've been using the simulation tools as well as data to develop the methods to search. One of the methods that we primarily employ is that we correlate the complex voltage data in the baseband using a match filter in time for each frequency channel independently. One of the interesting things we found was this first FRB 2020-0413B that does seem to show correlation signature, which is shown by the shadowy features on the right-hand side. And so we've been doing a lot of analysis on this event and trying to understand what might cause this. And so here are the main summaries of the findings. The first is we find the signature is only present in the power of the correlation and not in the phase of the correlation, which suggests that it's not entirely a coherent phase phenomenon. When we're analyzing the intensity spectra of these bursts in correlating getting the ACFs for the scintillation and trying to measure a scintillation bandwidth, we find that all these subcomponent bursts seem to have a similar scintillation bandwidth, which really suggests that they're all kind of unresolved, whatever's happening, and they're all getting propagated through a similar scintillation screen. Nonetheless, one of the things that strikes out about this burst is the morphology of it, in that one of the things we notice is that this branching morphology that you see is what leads us to believe that it might be a plasma lens FRB, in that if you have a lensing occurring near a caustic, you can model the frequency time morphology through this manner. But because we don't see the magnification that might be associated with it. So overall, is it lensing? Well, unfortunately, with no coherent phase detection, we cannot claim this is coherent lensing, but there is a correlation present. And what we interpret this correlation signature to be is that in a possible 2-screen lensing system, one of the screens is unresolved and is creating the scintillation, or the scintillation screen is the one that's consistent and has an unresolved point source to the other screen. Of course, without phase coherence, the argument for plasma lensing is only going to be a morphological one. And so we're trying to actively see if we can get a lens morphology fit to this event. And so as a final note, I do want to highlight that with our simulation tool and trying to understand and analyze this event, we're developing the search methods and trying to understand the ways we might be able to detect coherent lensing candidates and identify them in data. And we're hopefully using this to find a gravitational lens event in the future. So stay tuned.
Thank you, Zarif. We have time for one quick question before we move on to the discussion session. Yeah.
Hey Zarif, it's Lauren from McGill. I know nothing about lensing, but can